Berkeley lab was the first national lab. Livermore was spun off in 1952. So I'm going to talk about extreme weather in a changing climate. I think that's an important topic. It's an interesting topic. I call this slide the meteorological eye candy. And storms are cool. And models can simulate some kinds of storms. Up in the upper left is an atmospheric river, which is a kind of storm that delivers copious amounts of moisture from the tropics to the extratropics. This one's hitting California. The lower one below it is an extratropical cyclone delivering a lot of rain to the east coast. This radar overlay is a bunch of radar snapshots. Is a storm that was called the derecho. I actually experienced the aftermath of this. I flew in a red eye into Dulles right after this, and power was out everywhere. It was really hot. It was like 85 degrees at 7 o'clock in the morning and 102 and humid in Baltimore by daytime. I had relatives in both Ohio and in Virginia who lost power for multiple days from that very same storm. Had impacts across 4 or 5 states. And then the hurricane is Katrina, which of course the impacts of that were devastating. And that actually is the other reason to study extremes, is that the impacts are huge, and this is how most people are going to experience climate change, because you don't really care much about a 3 or 4 degree difference in the average. Tomorrow could be 3 or 4 degrees warmer than today, and you wouldn't do anything except maybe bring a sweater or not, or wear shorts or not. So it's the extreme weather where we really have some serious problems. The first is a picture of the dam is Folsom Lake. That's a great big dam in California, Northern California. You can see that it was very low in the winter. And Texas had some huge droughts recently. I'll speak a little bit about that one. And Snowmageddon was, why congressmen bring snowballs to the Senate chamber. Now, whether they had a snowball fight now, I'd really get interested. But no, only one guy brought one. You can't have a fight. And then this picture, I believe, is right behind the hotel, which was the Boulder flood in 2013. And all you have to do is ask anybody who works here about that event. They'll tell you about their impact. So this is a rough outline of my talk. I made this before I started writing the talk, and so most of this stuff is covered somewhere. I'll talk about some simple metrics that people use. I'd like to go into extreme value theory, partly because I really like extreme value theory. It's a very elegant statistical theory, but I think it also is a very practical one. Dan talked about it, so I'm not going to go into too much detail, but I'll tell you some maybe the gotchas, I suppose, is the way to put this, some ways that I like to use it. Storm tracking, but mostly, I want you to think, and this is important throughout, no matter what you do, whether you do extremes or not. Are these models fit for the purpose that you want to analyze? And the answer may be no. And there's a lot of publications out there in the refereed scientific literature where the answer was no, and they got through peer review anyway. And that's not a mistake that I would want to make. So keep that in mind, that sometimes the models really do suck. Quote an eminent scientist here. So the first practical thing that I want to tell you is about a set of indices that have been collected by a group that called themselves the Expert Team on Climate Change Detection Indices, and everybody says ETCCDI, except I always stutter on that and say something wrong, but they usually know what I mean. It's 27 different indices that were developed with the idea of using them to detect and attribute trends and extremes. And they were constructed basically to exploit the available observational data, which is often sparse, or in some cases not publicly released. There are some countries that feel that daily precipitation is a valuable quantity and you need to pay for it, and they don't want to release that. So they were convinced in some cases, to release some of the indices. They're not very descriptive of very extreme events, and some of them aren't actually extreme at all in some sense. But they're available, and they can be useful. I give you the locations for both observations, gridded. I think there's also station data there, and then model results and code to calculate them. But you probably don't need to use the code because most of the models have it's already been done. But if you had other runs, and maybe this should be done for the large ensemble, I don't know if it has been, calculate these indices. That would be a useful thing to do, and the code's sitting right there. Jana Silman, who is now in Norway, is the young lady who developed the code. So I want to get back to that fit for purpose thing. The four useful temperature indices that I like are TXX, TNN, et cetera. That's hot days and cold nights, and warm nights and cool days. So you basically are looking at the daily maximum temperature and say the annual maximum. And here is some work that Ben Sanderson just did, evaluating over North America these fields for various models, and also the mean temperatures as well, because we're using that. And you can see there's one model right there that's pretty close to the top. But you also notice that right here is a very closely related model that actually doesn't do so well. And you might ask what that's about, and I don't know. This could be a number of things. It could be that these ensemble sizes are rather limited, and so as we heard today, that can matter a lot. And these aren't trends; these are mean quantities. But if it's a 20-year period, Ben, is that right? 20-year, maybe 30. No, I did. I'm sorry. It's 20 or 30 years, and if you had a couple of those ensembles that were cool in North America, they could throw off your comparison with the observations quite significantly. But you can see that some models are just going to be bad. These ones down here, they're bad. I mean, there's just no way to put they're models you probably don't want to. You want to use some kind of model weighting probably. Here's some trends. These are unweighted multi-model trends that we made for the early draft of the national assessment. They'll be weighted by the time the next version comes around. And what I did is I picked just winter and summer, and so these are indicative of very hot days here, and very cold nights. And so you see the bitter cold nights will be much less bitter at the end of the century under this about 4-degree warming. But the hot days will be very hot. I mean, this is 5 degrees centigrade. So think about the hottest day of the year here in Boulder. I mean, how hot was it? What's the hottest day we had this year? 35. So that's going to be 40. I don't know what that is in Fahrenheit. That's a lot. That's pretty uncomfortable. 104. Is 40 or 35? 40. 40 is 104. Okay. I guess you can turn it off. This is 100 years from now. You're probably not going to need your hot stuff. But you also see that there's a big difference between winter and summer, and so I'll get to that point later. For precipitation, there's a whole bunch of indices that I don't have a lot of time for, but there's a couple that I do like. These three, but I wouldn't use them as annual, especially for precipitation. Now, when you annualize the temperature extremes, well, the maximum temperature is going to be in the summer, and minimums are going to be in the winter. Of course, you sort of already are doing that, at least in the mid-latitudes. but if you were to use annual quantities for precipitation, you really are mixing storm types. Winter storms are different than summer storms. And so I get really annoyed when I see changes in annual precipitation of any kind, because you're mixing all sorts of distributions, and mixing distributions is a bad thing. One thing we learned, and Dan mentioned this a little bit when we were looking at observations, that we had big differences in gridded precipitation extremes, and part of that, between data sets, part of that is that different stations in different parts of this country define the day at different times. In California, it was all at midnight GMT. In other parts of the country, it's 7 o'clock in the morning when the guy gets to work. And straightening that out was something I didn't want to do. And one day precipitation is kind of unusual anyway, because midnight Greenwich Mean Time could be right in the middle of your storm. And so, what does that mean? And so the 5-day, which has been collected, is a much more meaningful quantity to me, because there are very few storms that last more than 5 days. So this way you're going to get it all. And so you get that maximum. And consecutive dry days is not really extreme at all, but it's an interesting measure in areas that have a dry season. Is the dry season going to get longer or shorter? And that has impacts for agriculture. It has impacts especially on forest fires. Turns out that in the Pacific Northwest, this consecutive dry day measure has projected to become longer. And my young colleague Pardeep Paul has just shown that it has become longer. And I mentioned this to my dean at the University of California, and who's a forester, and he goes, well, that makes a lot of sense, because we have to spend so much more money on forest fire prevention. And the reason they're spending more money is not that they hired more guys, that they just have to hire them for another couple of weeks. And so, we actually saw the impact before we saw the meteorology. So here's that same kind of picture of model skill for precipitation, and here you really see some interesting behavior. So these models are, a lot more of them are really bad, and there's sort of an all of a sudden, threshold where, 10 of them are significantly worse than the median model. Then you have models like this one here from GFDL, which is pretty good at, it's all right anyway at the seasonal precipitation, but fails badly in the extreme. And where's our favorite model? It's right there. And this time, the difference between the FastChem version and the Cam5 version is pretty trivial. And I don't know why. So extreme value statistics. Dan talked about this. I want to talk about some of the practical things. The first thing when you're thinking about applying an extreme value theory is how you're going to exploit the data you have. And in other words, how are you going to sample the parent distribution of all values for its tail? And one thing that he talked about yesterday was block maxima. That would be like your annual max or your seasonal max, or your decade max if you'd like. And the underlying distribution, if you sample that way, is the generalized extreme value distribution. And the good thing here is that many of these indices that I spoke of are indeed block maxima already. And so this sampling work is already done for you. There are some limitations there, and I think there are many cases where you want to use the functionally equivalent peaks over threshold method, but there you have to have, with the underlying distribution there is a generalized Pareto distribution, which can be transformed back to the extreme value distribution, which we often do for convenience. But there you actually have to have a high frequency data set that you can sample from, because you're going to make, say, the 85 percentile thing. But regardless which way you choose to do this, there are some interesting quantities that you can calculate. And for instance, you can fix your period. So I'm going to show you some results later where we fix the period to be 20 years and ask what's the return value for 20 years and how does that change as the climate changes. So that's a change in the magnitude for a fixed rarity of event. Or perhaps more of an engineering kind of approach would be to ask what's the change in frequency for a fixed threshold. So let's say you design a sewer pipe. I've been working with San Francisco Public Utilities Commission on just this issue as they're spending $8 billion to rebuild the almost gold rush era sewer system in San Francisco. And how big do they need to make the pipes? Once you make those pipes, they're that way they're going to be. And so how big do you have to make them so that you're not flooding all the time? So then you would like a return, to calculate the return period for some fixed value of, say, daily precipitation. So as I mentioned before, a natural block size is a season, I think, especially for precipitation, but that might be too short in dry regions because, in 90 days you might not have any rain, much less extreme rain. And that may be true even for a year. As I mentioned, winter is different than summer. And when you're annualizing, you're basically mixing you're mixing the winter distribution and the summer distribution. This is not a good thing. What happens then is if you're fitting these extreme value distributions, you can get some unusual behavior, so you can get some artificially heavy tails, which can lead to incorrect results for return periods or return values. If you go to the peaks over threshold method, there is some arbitrariness here. You have to decide where your threshold's at. Now, if you're building a pipe and you know the pipe can handle so much rain, you're at your threshold. In Chicago, that's 2 inches a day. If you do more than 2 inches a day, raw sewage goes into Lake Michigan. So you want to know how often that happens. Pay a fine, and you have PR you have to deal with, which may be even more important than the fine. But from a statistics point of view, you want to be far enough down the tail that you're in what the statisticians call the asymptotic regime, so all these assumptions that you make about the behavior of the tail are valid, but you also have to have enough data. So if you have 10 years of data, it's not going to be enough. If you have 30 ensemble members, for the paper that I wrote with Claudia Tibaldi, we took 10 years from each, so we had 300 years. So the statistics were really good. So this is a value judgment that you have to make. And there are tools that can help you defend whether those decisions are valid, quality of fit kind of issues. And here's an example of what these distributions actually look like. The red one, the shape parameter that Dan talked about. So there's 3 parameters in both of these extreme value distributions. The shape parameter is 0. This is called the Gumbel distribution for historical purposes. And this one, the goes to infinity relatively rapidly. If the shape parameter is negative, is positive, that's the blue curve, it goes to, at infinity, the value is non-zero. And so it's an unbounded distribution. That's not physically realistic. Physically realistic distributions of precipitation or temperature are bounded. You cannot have a 500-degree day. And so then the shape parameter is going to be green. The negative one is green, and it actually is very bounded. And quantities like temperature, when you fit them, usually are well behaved in this regard. Precipitation is a whole other story. Often there's not enough data, and the best fit will be a blue kind of curve. That can lead to errors in interpretation, which are frequent in the literature, I'm afraid to say. So extreme value theory is a three-dimensional or three-parameter distribution, but there are constructs available to us where we can add more information via covariates, and they can be extremely useful, especially because extreme value theory assumes stationarity. Climate change is not stationary, obviously. And so if you're going to be stationary, you're going to have to take short time samples, which is okay if you have a 30-member ensemble, but if you have a 4-member ensemble, it's probably not so good. If you have one ensemble realization like you do for the observations, then it's very bad. And so covariates can remove that stationarity assumption, and you basically are adding more fitting parameters. And so some covariates that I think are useful and usually are linear in the location parameters, seems to be the best way to use them, are carbon dioxide concentration. This is to incorporate information about anthropogenic climate change. I like to think of this as nonlinear time. You know, when we first started doing this, we just used time as a linear function, but it's not really the way climate change works. But this seems to work very well. We also have used global mean temperature, but that has natural internal variability encompassed in it too, and so I've sort of moved away from that. But you may want to incorporate natural non-stationarity as well, and so your traditional indices like ENSO or NAO or PDO might be useful. And the original papers on this were by Jana Silman, actually, in her PhD thesis some years ago, where she used blocking and showed that that blocking in Europe and the change in blocking, or the change in cold extremes that were projected were very different if you incorporated blocking as a covariate, because when you think about it, a European cold wave is usually a blocked event. And so if you don't use this parameter, you're sampling too much in cold events that aren't really due to a blocking event. So this is all new. Experience is limited, and I think there's I like to do a lot more work on this area myself. So let's change topics a little bit and go back into this fit for purpose thing, argument. And I'm just going to use two examples because they're very different. This is from a paper by Oliver Angelil that has just been accepted in Journal Climate. It's an attribution study, an event attribution study. It's a survey of many different events. As an example, I picked seasonal high temperatures in this region of Australia. And what we've plotted here are two different observational estimates of the event itself. That's these horizontal lines. And then the model's distribution of temperatures in this season in this part of the world, and the two observational estimates of temperature there. And you can see that, and there's some error bars associated with it, and you can see that these distributions are acceptable. And so, in fact, we can use the model output without bias correction for this attribution study. And yes, there is a big influence. I'll talk a little more about event attribution, but since I'm on this particular event, the blue histogram is the distribution, or the sample rather, of simulations without a human component, and for this particular year. And the pink one is with, and you can see there's a clear shift in the distribution indicating a large change in both the probability of this event at the observed magnitude, or in the magnitude of it as a given variable. At the other extreme, forgive the overlapping of words, consider long period return values of daily precipitation in the winter. The observations over the United States for one of these observational data sets is as shown. You can see there's a lot in the west along the front range of the Sierra. There's some structure in the Rockies, and then this big large-scale precipitation maximum in the southeast. And here's three different resolutions of the finite volume version of CAM 5.1 running in the AMIP mode. And you can see at the standard resolution of 100 kilometers, or about 1 degree, it is too low. It doesn't produce events, a 1 in 20 year event of the right magnitude. And at 2 degrees, which is the many of the CMIP 5 models are 200 kilometers or even coarser. 100 kilometers is fine, the fine scale in the CMIP 5 archive. It's even worse. But at 25 kilometers, it looks pretty good. And so the model in the winter is doing a good job at producing the big storms. In the summer, this picture looks a lot worse because of issues with the convective parameterizations. This, of course, is model dependent, and there aren't many 25-kilometer models available, but I'll talk a little more about that for CMIP 6. So Reto was the CLA on Chapter 12, the convening lead author, he and Matt Collins, and I had the privilege of being a lead author and tasked with Julie Arblaster to say something about extremes. And so this is what we wrote. And the italicized language is the special confidence, the calibrated language of the IPCC. We wrote, it's virtually certain that in most places there will be more hot and fewer cold temperature extremes as the global mean temperature increases. It's almost a motherhood statement because it has the qualifier that global mean temperatures are increasing. That's why it's virtually certain, which is 99%. Under the RCP 8.5, that's the world warm one, we said it's likely that in most land regions a current 20-year high temperature event will occur more frequently by the end of the 21st century, at least doubling. And a current 20-year low temperature event will become increasingly rare. Now the basis for this statement was from extreme value statistics. This was done by Slava Karin at our commission by us for this for the report. And here are for the two different scenarios of 2.6, or three different scenarios of 2.6, 4.5, and 8.5 of the hot day, 20-year return value, and the cold night. And you can see that over much of the multi-model mean is 5 to 7 degrees over most of the mid-latitudes. So whatever your 20-year event is. And we chose 20 years. 20 years is it was sort of an interesting time interval to think about, partly because that was fit well with the data we had. But I like it because 20 years is about as long as you're going to remember. It's not the once-in-a-lifetime event, but it's probably the warmest, most uncomfortable day you remember. And so to put it just in some kind of personal context, and so it leads to the phrase, the soundbite that today's rare hot events become commonplace. And indeed, the 20-year return value of today, for this on the RCP 85 scenario, is 2 years or less, pretty much everywhere over land. Many places it's less than 1 year. And again, you see that the winter colds change dramatically. And so those really super cold days basically don't happen anymore. So what do we say about precipitation? This is a lot harder. And so I'm not going to read the statement because it's a lot weaker statement. What I want to tell you is some of the thought that went into it. I wrote, the models are judged to not be of high enough quality to justify pictures like I just showed you. That judgment was my judgment. And I had support from other people that were, when we met cross chapters about extremes. But there was pressure from the powers that be to put something in. So I put something in. And it's something from the paper that went along with this. And it's difficult to explain. And it's difficult to explain on purpose. Because pictures like this take on a life of their own. And will have a lot of spin to them, either from denialists or from alarmists. And I didn't want that for precipitation. And so what we did is the picture of the change in the 20-year return value of precipitation is normalized by the local temperature change. So it's divided by the average change in temperature at that location. It's not without information. What it's telling us is that these rare events in the models are largely dictated by Clausius-Clapeyron scaling, which is about 6 to 7% per degree warming. And the Clausius-Clapeyron relationship is a 19th century empirical relationship that tells you about the saturation, specific humidity of air at a given temperature. And this was a very deliberate choice to downplay the attention paid to this figure because of because of the previous figure that I showed you with the high resolution and how poorly extreme precipitation is simulated by CMIP 5 class models. So, and then the other picture is even more difficult to explain because it's a change in the return period of today's 20-year return value divided by normalized by the temperature change. And so I'm not actually sure even what that means. I think if I'd thought about this a little more at the time, I wouldn't have put it in at all. But Slava liked it. So now I've been involved in the second with national assessment with Ben, and the third, and now the fourth with this band. So both bands. And I could not get away with this for them. They really wanted something. And I was not going to put in change in return value. So we did something that is actually part of the event attribution literature, which is called the risk ratio, but the powers that be, the national assessment, called it even something worse, which is the frequency change multiplier, which is really the ratio of today's return period divided by, I have this backwards again. This equation's upside down. No, this is right. It's a change in today's return period divided by in the future, or it's the future probability divided by the present probability of an event of a specific magnitude. And Xubin Zhang and I had some discussions, and we thought this might be a little bit more stable to errors in model errors. And so this is what it looked like for the United States. So that it's telling us as that for a today's 20-year event, it will become this color is 3 to 4 times more likely in the future. So its return period is 7 instead of 20 years. And this concept of risk ratio is also used in event attribution. We'll talk about that. So I tell you this story, and and it's being filmed, I guess. And, it is some dirty laundry here, but the IPCC is composed of individual scientists who have to make individual decisions that have ramifications of their own. There are pressures to do things sometimes that you don't want to do, but you got to do something. And so this was the best I could do to do something that I thought was scientifically justified, that wouldn't be abused. And in fact, I've never seen this picture in a newspaper. This one I have. So, my picture on the high resolution showed that you really need this to accurately simulate intense storms. And this 25-kilometer resolution seems to be a very different class of models than 100. And that's a good thing because computers are still increasing in speed by Moore's law, and they will for at least another decade. And so there's a sub-project in CMIP 6 called high-res MIP, and there'll be something when this finishes of the order of 5 to 10 models in the 25-kilometer range. So we can actually do multi-model kind of analyses. The database is larger, and because the storms are more realistic, the sub-daily output becomes more interesting. So the database doesn't change just by the horizontal resolution, but also because it's more interesting at high frequency, you want to save more stuff. And so the CAM5 actually, I think, is best in its class for simulating hurricanes up to Category 5. And as it showed, it had better precipitation statistics. And when I did the calculation I'm going to show you a simulation of, it took me 2 days to make a year. Now I'm doing 1 day per year on the same number of processors, which is about 8,000. And the next machine is going to be that much faster. And so these are going to become more routine. It won't be too long before we're at 10 years per day. And a lot of people in this room are young enough that by the time they're my age, this stuff you do on your phone. So here's like what an astronaut would see looking at the planet, if he was looking in this projection anyway, or she was. It's total integrated water vapor from the top of the atmosphere down to the bottom. And you can see the hurricanes. I picked this during hurricane season. But you see a lot of other structures. And if you're in the back of the room, you may not see it as clearly, or if you're as nearsighted as I am. But you see atmospheric rivers all over the place. You see very sharp gradients in moisture. I'm going to stop this one here. The upper panel is the same model, but at 200 kilometers. In your back of the room, maybe they look the same. And that's kind of good, because it means that all the conclusions that IPCC made based on 200-kilometer models in CMIP 3 and 5 and the U.S. national assessments about the large-scale climate change are pretty defensible. But you can see that, as you get to local details and the intense storms, that the 200-kilometer model is basically not realistic. If we lived on that planet, on planet 200-kilometer CAM, there wouldn't be any violent storms. Every day would be kind of overcast. We might be a gloomier race than we are. So that's that. Then we have much more interesting weather, including hurricanes. Now this is a plot of all the tracks of all the storms with observations at top and the simulation at the bottom. And there are differences. There are important differences. If I peel away the tropical storms, which were in purple, and we just look at hurricanes, Category 1, you see a little bit more detail. And the biggest bias that you see here, that I see here, is there are too many storms in the center of the Pacific. But it's still pretty good, and it gets the right number. And in fact, it even makes Category 5s and 4 and 5, which are the intense hurricanes, which is pretty remarkable. So with the advent of these kind of models, these storms are more interesting. But in order to say anything about them, you have to find them. That's what we did in order to make that plot. I originally thought I could watch movies. That's the quick way to insanity. So you have to have tools to do that. And our group has developed this thing we call TICA, which is basically based on an algorithm called MapReduce that is highly parallel. In fact, as a stunt, we ran it on Mira, which is a machine in Illinois on 750,000 processors. I typically use 10,000, but even 100 is a lot better than 1. And we can reduce the time to solution to find these tropical cyclones from weeks to hours or maybe a day or two. This is almost ready for release to the public. I think it would be useful to have here at NCAR, and we're happy to help with that. We have an extratropical tracking cyclone in it as a beta version and an atmospheric river identification. Hi, Christine. That is, I would say, pre-beta. We've had some problems there. Another venue for tracking storms do feature identification is something called supervised machine learning, and we have a recent paper that demonstrates that this works. It will be some years, though, before this is turned into a useful tool. And that is actually very computationally expensive. So let's talk about hurricanes. So do CMIP 5 class models have any value in the projections of future tropical cyclone frequency? And so one thing to ask is, does a low resolution model simulate the behavior of the high resolution model? And the high resolution model predicts, if you look at the blue one and the red one, this is the global number of storms from category 0, that's tropical storm, to category 5. It goes down from about, which is almost the right observed value, of 85 per year globally to 70. That's a big decrease. And then the Cat 4s and 5s goes up a little bit. And in fact, the most intense storms are more intense in the warmer world. But the low resolution model shows exactly the opposite. Makes more storms in a warmer world. So my conclusion is no. Direct tracking of storms will give you the wrong answer. Because, and I think this is because it's actually only seeing the weak, you're limited by the weak storms. You can't see the weak storms at 100 kilometers because all the storms are so much weaker that you're only seeing 8 per year. Well, that's about the number of intense hurricanes that are in the high resolution ones. So a category 1 storm at 100 degree, at a 100 kilometer model is actually your most intense storm. And all those ones that should be there are just in the noise and you can't distinguish them. So you can't use these models in this way. But you could ask, are the bulk characteristics of CMIP 5 class models of any value? And Kerry Emanuel has introduced something called the maximum potential intensity index, which is the intensity of the perfect storm. So now we're talking about the extreme hurricanes. And indeed, the 1 degree model predicts the same behavior for the change in this maximum potential intensity index as the high resolution model. And this is consistent with what we found in the high resolution model, that the most intense storms become more intense. So yes, CMIP 5 class models are fit for purpose in this particular aspect. Now there's another index from Kerry called the Genesis Potential Index, and this is to predict how many storms there are. Well, remember, the low resolution storm model said there'd be more, the high resolution model said there'd be less, and in fact, both models predict from an increase in the Genesis Potential Index. And so it's actually wrong. The Genesis Potential Index is not a fit-for-purpose metric. And what's happening there is it actually is correctly produced. It's correct in its name. It's the potential for cyclogenesis is indeed increased in a warmer world. But it's not realized because a warmer world is more stable. There are fewer disturbances that can run through the cyclogenesis region to develop into hurricanes. And so, no, the CMIP 5 models are not applicable for the cyclogenesis question, but it's not their fault. It's the fault of the index if it doesn't have information about the stability of the atmosphere. I mentioned that data sizes are large. We did a case study. This was the 750,000 processor stunt. But there was science behind it. We wanted to track extratropical cyclones in all the historical RCP 85 and pre-industrial control experiments to do a detection and attribution study, which is underway. I estimated this, and it turned out to be right. It was 160 terabytes of model output. I knew that I would not be able to do that. I don't know how many how many folks here have run ESGF. I just knew it wasn't going to happen. So I talked to Eli Dart. He's a network professional working for ESNet. It took him 3 months to download it. But I asked him he was thrilled to do it because he then did all the technical analysis of the network. And this is a plot of data transfer rates from all the different centers. You can see it varies wildly. And the time to download a terabyte range from a couple hours to 2 months. This will improve when a tool called Globus is fully enabled. Use Globus. Avoid wget, which is the way that ESGF will default to, if at all possible. Because when high-res MIP comes, for using our tracking algorithm, it's 10 terabytes per decade per model to do hurricane tracking. Now, as an aside, this is Netflix rate to my house. And so only a few of the centers can transfer to our computer center, which is on the network, the ESNet, which is the fastest network in the world, faster than I get Comcast wireless in my house. So there is clearly something structurally wrong with the system we have. There's a paper behind this, and nobody wants to touch it. Stream event attribution. Oh, we're almost done. I might skip this. I'll fly through it. So this is the question people always ask. Are the Louisiana floods climate change? Lots of people say all sorts of things. A lot of it's wrong, and it's because models are not necessarily fit for purpose. But you can use, if the models are judged to be fit for purpose, you can use the CMIP5 ensemble and extreme value statistics, or you can use other ensembles that are also available. Consider these three, and heat waves are particularly amenable by CMIP5 models. These three heat waves were massive and had massive impacts, 2 in Europe and 1 in Texas. Methods are detailed in this paper that Pardeep wrote that's in a book that is online. We talk about the risk ratio. I talked about this frequently change multiplier thing. It's basically the probability, this context is the probability of an event of that magnitude, that say the Texas heat wave, as we estimate from models in the real world versus model in the not real world. So it would be the historical ensemble versus the historical NAT ensemble, for instance. And we found that for these three heat waves, the best estimate of the human contribution is to double the odds of these events at the time it occurred. And into the future, the risk of that event actually could get significantly worse. So the European heat wave in 10 years from now is 35 times more likely than it would have been in the pre-industrial time. And by 2040, it's basically happening 9 out of 10 years. That's what this distribution over here, plot over here is showing that the probability of that event is 90% by 2040. And that's more or less independent of scenario. There are other data sets. The one that we've provided is called C20C+. Now, CMIP5 is 2 different kinds of simulations. You have prescribed emissions and prescribed concentrations that would dictate how the climate has changed. We've had actually this kind of experiment for a long time. It was called AMIP, where you prescribe the temperature. You prescribe the sea surface temperature and the sea ice. And we're now using that both for retrospective analyses as well as future analyses. And the retrospective analysis is C20C+. This website here describes it. There's 5 to 10 models available, 5 now. Ensembles are large. We have some years we have up to 400 members for both the real world and the counterfactual world without humans. And what we're doing now is a project called HAPPY, which stands for, it's not very happy actually, it's half a degree of additional warming, projection, prognosis, and impacts. And this is a response to the Paris COP21 agreement, is what is a 1.5 degree world really like? And so through pattern scaling, we've taken the RCP 2.6 experiments and constructed an estimate of what the SST might look like then. I have no results to show you. This is work with Dan Cooley. I think it's also very interesting and state-of-the-art. Is extremes are always actually, or almost always are, combinations of effects. And so what can we do about multivariate extremes? The impacts are different, so hot, dry, and windy. In California, Santa Ana's would be wildfires. Hot, moist, and stagnant, people in cities die. And in fact, this scatter plot is sort of the edge of the distribution in relative humidity and temperature space of the deadly heat wave in Karachi, Pakistan last year. And the asterisks are the actual values. And what you see is that the temperature wasn't really a record temperature by any way, shape, or means, but the combination was a rare event in that it's at the edge of this scatter plot. And so, and that's why it was so deadly. Useful tools. If you're really interested in extreme value theory, you got to get this book. It is written for us. It's not written for statisticians. There's still a lot of statistics in it, but it is targeted towards people like extremes with a capital R was mentioned yesterday. That has a lot. This means that you don't have to code the stuff up that's in Cole's book. It's already written for you in R. And then we have a Python wrapper around a lot of these extremes functions that are of particularly non-stationary problems that are particularly interesting to me, but they might be to you as well. As I mentioned, this storm tracker is going to be ready. So I'll just leave that up. Do we have time for questions? Okay.
So we have time for questions. The only area closes at 1:30.
And I'll be at lunch too, so
we can start having a few questions now, and then.
Right done. I wrote it during Jerry's